Welcome to the essential world of measures of dispersion. While central tendency tells us where our data clusters, dispersion reveals the whole story: how spread out, how variable, how scattered our data points really are. Think of dispersion as the personality of your dataset. Two datasets might have identical means, but completely different characters, one tightly clustered like a disciplined army, another wildly scattered like excited children at recess. Understanding dispersion is crucial for risk assessment, quality control, predicting outcomes, and making informed decisions in business, science, and everyday life. Dispersion measures the spread or variability of data points around the center. Imagine two basketball teams with the same average score of 50 points per game. Team Blue consistently scores between 48 and 52, reliable and predictable. Team Red's scores range from 35 to 65, unpredictable and volatile. Both have identical means, but completely different risk profiles. Team Blue offers consistency, while Team Red brings excitement but uncertainty. This is why understanding dispersion is crucial for making informed decisions in sports, business, and life. We have 4 powerful tools to measure dispersion, each with its own personality and purpose. The range is our quick and dirty measure, simple as maximum minus minimum, giving us an instant sense of spread but easily fooled by outliers. Variance is the mathematical workhorse. It uses every data point to calculate the average squared deviation from the mean, providing a comprehensive but sometimes hard to interpret measure. Standard deviation is variance's user-friendly cousin. By taking the square root, it returns to our original units and becomes the most widely used measure. Finally, the coefficient of variation is our diplomat. It makes dispersion relative, allowing us to compare variability across completely different scales, like comparing the consistency of a basketball player's free throws to a company's quarterly earnings. Let's start with the range, the most intuitive measure of dispersion. The range is beautifully simple. Just subtract the smallest value from the largest value. It's like measuring the wingspan of your data. How far does it stretch from one extreme to the other? The range gives us instant insight into the total spread, making it perfect for quick assessments and easy to communicate to any audience, regardless of their statistical background. Let's calculate the range for daily temperature readings over 10 days. Our temperatures range from a cool 18 degrees to a warm 35 degrees Celsius. The minimum temperature of 18 degrees represents our coldest day, while 35 degrees was our hottest. The range calculation is straightforward. 35 minus 18 equals 17 degrees. This tells us our temperature varied by 17 degrees over this period, a substantial daily variation that might influence everything from clothing choices to energy consumption patterns. The range has clear advantages and limitations. On the positive side, it's incredibly easy to calculate. Even a child can find the biggest and smallest numbers and subtract them. It gives an immediate sense of your data's total spread and is perfect for setting quality control limits or doing quick data exploration. However, the range has significant weaknesses. It only uses 2 data points, completely ignoring everything in between. A single outlier can make your data appear much more variable than it actually is. The range also tells us nothing about how the data is distributed between the extremes, are most values clustered near the center, or spread evenly. Variance is the mathematical foundation of dispersion measurement. Unlike the range, variance considers every single data point, measuring how far each one deviates from the mean, squaring those deviations to eliminate negative values, then averaging them. We have two versions. Population variance uses the entire population and divides by n, while sample variance divides by n-1 to account for the fact that we're estimating a population parameter from a sample. This degrees of freedom adjustment prevents us from underestimating the true population variance. Let's work through variance calculation step by step using a simple dataset. Our 5 values have a mean of 6.0. For each value, we calculate its deviation from the mean. Then square that deviation. Value 2 deviates by -4, which squared becomes 16. Value 4 deviates by -2. Squared becomes 4. The center value 6 has 0 deviation. Value 8 deviates by +2. Squared is 4. Value 10 deviates by +4. Squared becomes 16. We sum all squared deviations to get 40. Then divide by our sample size of 5 to get a variance of 8. Notice how squaring the deviations gives equal weight to values above and below the mean. Why do we square the deviations instead of just using their absolute values? Squaring serves two crucial purposes. It eliminates the problem of negative and positive deviations cancelling each other out. And it gives progressively more weight to larger deviations. A data point that's twice as far from the mean contributes 4 times as much to the variance. This mathematical property makes variance especially sensitive to outliers, which can be both an advantage and a limitation depending on your analysis goals. Standard deviation is simply the square root of variance. But this simple transformation makes it incredibly practical. While variance is measured in squared units, like squared dollars or squared meters, which are hard to interpret, standard deviation returns to our original units. If we're measuring heights in centimeters, the standard deviation is also in centimeters. This makes standard deviation much more intuitive and easier to communicate than variance, while preserving all the mathematical rigor that makes variance so valuable for statistical analysis. Standard deviation becomes truly powerful when we understand what it means in practice. For normally distributed data, standard deviation follows the famous empirical rule. Approximately 68% of data falls within one standard deviation of the mean, 95% within 2 standard deviations, and 99.7% within 3 standard deviations. This rule helps us understand how normal or unusual any particular data point is. A value more than 2 standard deviations from the mean is quite unusual, occurring less than 5% of the time in normal distributions. Here's how standard deviation works in quality control. If a factory produces bolts with a target length of 10 centimeters and a standard deviation of 0.1 centimeters, we can predict the distribution. 68% of bolts will measure between 9.9 and 10.1 centimeters, within acceptable tolerance. 95% will be between 9.8 and 10.2 centimeters. Any bolt shorter than 9.8 or longer than 10.2 centimeters represents a quality issue, occurring about 5% of the time. Bolts outside the 9.7 to 10.3 range are extremely rare, only 3 in every 1,000, and indicate serious process problems requiring immediate attention. The coefficient of variation is dispersion's diplomat. It makes different datasets comparable by expressing standard deviation as a percentage of the mean. This relative measure allows us to compare variability across completely different scales and units. We can now meaningfully compare the consistency of a basketball player's free throw percentage to the stability of a company's quarterly profits, or the reliability of rainfall patterns to the predictability of stock returns. The CV levels the playing field, making dispersion universal and comparable. Here's where the coefficient of variation shines. Consider two investment options. Stock A has an average return of $50 with a standard deviation of $15, while Stock B averages $200 with a standard deviation of $40. At first glance, Stock B seems much riskier with its higher standard deviation. But when we calculate the CV, Stock A has 30% relative variability while Stock B has only 20%. Suddenly, Stock A is revealed as the riskier investment relative to its return. The coefficient of variation uncovers the true relative risk that absolute measures would miss. Here are general guidelines for interpreting coefficient of variation. A CV below 15% indicates low variability. The data is highly consistent and predictable. CVs between 15% and 35% suggest moderate variability, reasonably stable but with some fluctuation. Above 35% indicates high variability, quite volatile and less predictable. CVs exceeding 100% represent extreme variability where the standard deviation actually exceeds the mean, indicating very unpredictable, erratic behavior. Let's compare all four measures systematically. The range uses original units but is extremely sensitive to outliers, making it perfect for quick exploration but unreliable for detailed analysis. Variance uses squared units which are hard to interpret, but provides the mathematical foundation for other statistics. Standard deviation returns to original units while maintaining mathematical rigor, making it the most versatile general-purpose measure. The coefficient of variation uses percentages and has moderate outlier sensitivity, making it ideal for comparing across different scales. Here's when to use each measure. Use range for quick data exploration, setting initial control limits, and simple reports where ease of understanding matters most. Variance is essential for advanced statistical calculations like ANOVA and regression analysis, where its mathematical properties are crucial. Standard deviation is your go-to measure for general analysis, quality control, and risk assessment. It balances interpretability with statistical rigor. Use coefficient of variation when comparing investments, suppliers, or performance across different scales where absolute measures would be misleading. In finance, dispersion measures are crucial for risk management. A portfolio manager comparing three mutual funds sees that the conservative fund returns 6% annually with 2% standard deviation. The balanced fund returns 8% with 4% standard deviation. And the aggressive fund returns 12% with 8% standard deviation. The coefficient of variation reveals that risk increases proportionally with return. Each fund has similar risk-adjusted performance. Standard deviation helps quantify the probability of losses, while CV allows comparison across different return levels. In manufacturing, dispersion measures enable proactive quality control. This electronics factory monitors component dimensions using standard deviation for statistical process control and range for quick checks. Resistors show good consistency within specifications. Capacitors have higher variability, suggesting process adjustment is needed before defects occur. Transistors show a wide range, indicating possible outliers that need investigation. Standard deviation allows prediction of defect rates, while range provides immediate alerts for operators on the factory floor. In healthcare, dispersion measures help evaluate treatment consistency. Comparing 3 blood pressure medications, drug A shows the highest variability with a 53% coefficient of variation, unpredictable results that concern doctors. Drug B has the lowest CV at 25%, indicating reliable, consistent results even with moderate efficacy. Drug C offers high efficacy but with moderate variability. For patient safety, Drug B's consistency might outweigh Drug C's higher average effectiveness. Dispersion measures help doctors balance efficacy with predictability. Let's address common mistakes. First, don't assume standard deviation works for all distributions. It's most meaningful for normal data. For skewed distributions, consider alternatives like median absolute deviation. Second, never compare absolute dispersion measures across different scales. A $1,000 stock price fluctuation isn't comparable to a 5% return fluctuation. Always use coefficient of variation for cross-scale comparisons. Third, avoid using range for large datasets where outliers become more likely. Standard deviation provides more robust analysis for larger samples. Follow these professional best practices. Always visualize your data distribution first. Histograms and box plots reveal whether standard deviation is appropriate. Use multiple measures together for comprehensive analysis. They each tell different parts of a story. Report confidence intervals alongside standard deviations to show uncertainty. Consider your sample size. Small samples make dispersion measures less reliable. Choose measures appropriate for your context and audience. Range for quick communication. Standard deviation for technical analysis. Finally, always document your assumptions and limitations to maintain analytical integrity. As we conclude this comprehensive exploration of dispersion, remember these key insights. Dispersion completes the data story that central tendency begins. Together they provide full understanding of your data's character. Each measure serves different purposes, so choose based on your specific needs and context. Data distribution should always guide your choice. Normal data suits standard deviation, while skewed data might need alternatives. The coefficient of variation is your key to meaningful comparisons across different scales. Professional analysis combines multiple measures for complete insight rather than relying on any single statistic. Most importantly, understanding why these measures work and when to use them is far more valuable than simply memorizing formulas. Let's crystallize our understanding with this final summary. The range provides quick overview, simple spread from minimum to maximum. Perfect for initial data exploration. Variance serves as the mathematical foundation, average squared deviations that enable advanced statistical analysis. Standard deviation offers practical power. Variance returned to original units for intuitive interpretation and broad application. The coefficient of variation acts as the universal comparator, a relative measure that enables meaningful comparison across any scale. Master these 4 measures, and you'll have the complete toolkit for understanding data variability. Your journey into dispersion analysis begins now. You are equipped with both theoretical understanding and practical wisdom to tackle real-world variability challenges. Every dataset tells two stories, where the data centers and how it spreads. You now have the complete toolkit to hear both stories clearly and make informed decisions based on full understanding. Go forth and analyze with confidence. Remember, you're not just calculating statistics, you're uncovering the true nature of variability that drives risk, quality, and performance in our world.